So given this situation, we could use graphical analysis to solve this. And so here's one way to get at it. So we're always going to need velocity time and acceleration time graphs. We probably should have them with equal plus and minus space above and below, but for this one I know where I'm headed, and so I want to kind of make it simple. Given the information, what is something that we know other than the height of the building? Gravity is accelerating this, and gravity is accelerating at a constant rate. And in fact, for the sake of simplicity, we're just going to call this 10 meters per second every second. Instead of 9.81, simple number crunching here, we're just going to use 10. All right, makes things simpler for what we're trying to do. And we know that there's some time this is going to be the time where it reaches the ground. All right. So one of the things that's helpful in this graphical analysis game is kind of plan out the way you're going to graph this. All right. So all of these are going to be solved by graphing rather than equation hunting. All right. So I know that acceleration due to gravity is 10. However, I do want to have you consider, so there's a building, here's the ground, height is 96 meters. If the ball is dropped from the top of the building, I have two choices. The top of the building could be 0, and the ground would be minus 96, if I want to have up is positive and down is negative. I could define the top of the building to be 0, and down is positive. So given the way that I've graphed acceleration, that's what I've done. Down is the positive direction, going from 0 to 96. There's a number of ways that I could start this or set up my system, and it's totally arbitrary and totally based on what you want to do to make your life easy. All right, and so I'm going to go easy because guess what? From the ball's perspective, we're speeding up. Okay, we're getting faster and faster and faster. Well, if that's my assumption, and it is, the ball's dropped. What's its initial speed? 0. And since it's got a constant acceleration, it's going to have a linear change in speed. And then when it hits the ground, that will come to an abrupt stop. And its acceleration will go to 0. Here's the thing that when we get to gravity full on, we'll remind you of this. It's not that gravity stopped doing its work on the object. The object's acceleration is no longer positive. In fact, it's 0 now that it's on the ground, but gravity is still, quote unquote, accelerating it. The field strength of Earth's gravity is still influencing a force field effect on the object, even though it's not moving. The ground is winning once it hits the ground, minus the dent. All right. So we have this situation. And notice that this question, well, it's not a question, it's a statement, isn't it? I didn't ask you to compute anything, and that's the point. Here's a situation, model it. Take the information that you have and generate as much information as you can. That's what we're doing in this assignment. So what do I know? Well, uh, as I recall, the area under acceleration time graph is delta V. Second zeroth law. Well, we happen to know that acceleration is 10, so I have 10 delta t, but I can't improve that equation any more than that, so I move on. Up here, we know that delta y, I'm going to go ahead and use XYZ stuff for this. It's vertical, so we'll use y. The area here is going to be 1/2 delta v delta t. Well, delta v was that, so I could move that 10 delta t in for delta v, and I'll get delta y equals 1/2 10 delta t times delta t. But this is also delta y, the 96. That's the height of the building. So 96 equals, we could go ahead and make that a 5 delta t squared. Now, at this point, I'm going to say this. Does anybody have an idea what I mean by PID? Physics is done. Why am I telling you this? Well, at this point, now it's a math problem. We have encoded everything that can be encoded in terms of the laws that govern this, and now it's a computation. All the known quantities are put in the axioms, and here it's just done. So assuming we did the physics right, all we got to do now is get the math right. Well, this should be relatively simple. 90, delta t is just going to be the square root of 96 over 5, which is, I think, 4.4 roughly when you do the math. So now we have obtained this piece of the puzzle that it took 4.4 seconds for a ball to fall as far as a football field is long, because 96 meters is essentially 100 yards. So a 300-foot tall building. So if you think about it, 1001, 1002, 1003, 1004, yeah, I buy it. Okay, might take a little bit longer because there's some air drag, small amount of air drag on it. But this is in the ballpark. This passes the smell test of believability. So time of flight. We obtain time of flight from the given information. Now what would be a useful piece of information to obtain? What else would be good to know that we don't know? Well, we know the position change. It went from 0 to 96. So that was given. We knew its acceleration. We just found the time of flight. What else do we not know? The speed. So we could take this time and plug it in over here. So this means I have 10 times 4.4. So this is going to be roughly 44 meters per second, which is roughly 96 miles per hour. So that's cooking. I want to stand back from that. I don't want to catch the ball or have it hit me in the head or anything like that. It's probably going to be a little bit less than 96 because of, like I said, air drag, but it's going to be moving pretty darn fast. All right. So that's how we would use graphical analysis to solve this relatively simple problem. All right, so we are told that the train has an acceleration of 3, and I'm just going to kind of skip the units. All right. And so if it starts from rest, that means it starts from a 0 speed, and if it's got a constant acceleration, it has to be those two graphs. Constant acceleration has to be a horizontal flat line. It was positive at 3, so we labeled it that way. If the acceleration is constant positive, the velocity has to look the way it looks on this graph. All right? So, nice thing here is we know that delta V equals A delta T, which means delta V is going to be 3 times 9, or 27 meters per second. Delta X, we'll assume it's horizontal, would be 1/2 delta V delta T, which means it's 1/2 of 27 times 9. Anybody compute that number yet? 121.5 sounds right. Meters. So easy peasy. All right. Now what we could do, the equation hunting method would say, all right, you've been given the fact that acceleration is 3, that delta t is 9 seconds, and you would say to yourself, oh, I think there's this rule that says delta v is a delta t. That's equation hunting. So that must mean delta v is 27. And then you would say, oh, and there's another rule that says delta s is, let me use x, is v naught delta t plus half delta v. Actually, it would be at squared. And you would say, well, it didn't have an initial speed, so that's 0. So my delta x is just 1/2 at squared, and you'd go 1/2 of 3, 9 squared, and you'd go through some business. So your textbooks will show methods like that. All right? And that's easy because you say, oh, I have 2 out of 3 things in an equation, so I'll use that equation. That's not doing physics, that's doing math. I need you to do physics. All right? So over here, we were able to do physics with the graphing because we were pulling the laws, representing the motion, et cetera, in a graph. All right? So these are 2 really easy ones. All right, so let's think about this choo-choo train problem a little bit. So we start off with a positive 2.2 acceleration for the first 14 seconds. Then it goes to constant speed. That would be 0 acceleration. Then it says it slows down at a rate of 2, but that means -2. Slowing down at 2 means -2. So this will drop down into the negative zone here. And then we presume it comes to a stop. It would be great if stepping on the brakes eventually let your car go backwards, you would never need gas again. Unfortunately, brakes don't work that way. You actually come to a stop once you're out of speed, so to speak. Now what we can do is these flatline constant acceleration graphs can only be, the velocity versions are associated with them can only be one way. A positive acceleration means a change in speed like that. Constant acceleration means flatline speed. And then deceleration to a stop would mean that. So these time regions are laid out for us. So that would be the velocity and acceleration graphs that go with this problem. A period of positive acceleration with a positive speed and change, a period of no acceleration with no change in speed, and then a negative acceleration with a negative change in speed. All right? So I trust that you were able to obtain those graphs. And so let's get at it. So here, this change in speed, number 1, we know it's acceleration times time, so we can just write 2.2 times 14. What's the change in speed? Not all at once. 30.8 meters per second. So that's what we could just put up here, 30.8. Well, that means that this first change in speed, I could write 1/2 30.8 times 14 seconds. Anybody compute that one yet? What's our displacement? How much? 215.6 sounds good. And then this other change in position or displacement would just be the speed, because it's a rectangle, times the time change that is associated with it, which is 40 more seconds. And this one turns out to be, what, 1200 something? 1232. There's nothing to compute. We already know it's zero acceleration down at the bottom because it's constant speed. Don't need to do that. There's no area there. You don't need to compute what's obvious. And then this last part. Well, let's look at the change in speed for this third region. Would be what? Well, it would be a -2 times, well, I don't know. Do I? I could put t minus 56 here. All right. I do know the change in speed, though. What's the change in speed? It's a negative 30.8. If you look up at the top, okay, it's a negative slope. It goes from 30.8 to 0. That change would be a negative 30.8, which works out nicely because then I'll get a positive time here. This is what, 15.4 seconds? So now I know how long this part up here goes. Yeah.
Wait, I'm sorry, I don't understand how you got t minus 50.
You don't understand what?
The t minus 50.
6.
Oh, t minus 6.
Oh, I said 54. I'm sorry. Let me. In fact, I'm just going to switch it to delta t. It would be t minus 54, not 56. Just typo. It's a delta t there.
Delta t. Oh.
I initially meant to write t minus 54, but I wrote a 56. It's just a mistake. So the change in time for this little region here, 15 seconds. All right. So now, or 15.4 seconds. So now this delta x3 up here, I can compute what it's going to be. And this is where you kind of have to know what you're paying attention to. I have to use the magnitude of the speed change because it's a positive displacement. All right, so the 30.8 in here, and this, I forget what this works out to be, but it's going to be not much more than the first one. 237, 0.2 or whatever. And so now we have all of the regions of displacement, and if we wanted to have a delta x total, we would just add up the delta x's. Okay? And that would just be, adding a few things up. But we computed the speed changes. We only needed to get one speed change because it's just going to be the magnitude is not going to change in the last region. So this is a problem that's really just several in a row, several small ones in a row.